You're working on Newton's second and third law lab and notes, and I'm going to do a tutorial here on Newton's second law, which should cover your page 1 and page 2 of your notes, and then probably have another YouTube where I cover the lab section of Newton's second law, which would be pages 3 and 4. So, and then pages 5, 6, 7, and 8 I'll cover in different tutorials. So, this is Newton's second law of motion. If you missed class, you missed a chance where a student sort of self-discovered Newton's second law of motion, and so you're going to miss out on that opportunity. But you do get a chance here to use the notes to review. So, if you're looking at your first question, asks you what is Newton's second law of motion, and one way to state Newton's second law of motion is right here. The acceleration of an object depends on the object's mass and its net force. So we can write that as an equation in this way right here. So that's Newton's second law of motion. So what it's saying is that acceleration depends on the force acting on the object and the mass. So if we use the equation, we can figure out key point number 1. Actually, we can use common sense, and we could use the equation to prove it to ourselves. So for example, if we increase the force acting on an object, in other words, we hit it twice as hard or push it twice as hard, what would happen to the object's acceleration? And my guess is, just through common sense, most of you would figure out that it in fact increases. Another way you could sort of prove that to yourself is use the formula. Okay? Plug in some fake numbers. For example, if we had a force of 4 and a mass of 2, it would accelerate. 4 divided by 2 is equal to 2. However, if we increase the force, let's say we increase the force instead of 4, we increase it to 8. So instead of having an acceleration of 2, we would take 8 divided by 2, and that would equal 4. So we would double its acceleration. So increasing the force increases the acceleration. All right. Let me erase that. And erase that. Sorry for the delay. And then finally, what happens if we, key point number 2, what happens if we increase the mass of the object? What's going to happen to the acceleration? Again, think of like a semi-truck trying to accelerate down the road versus a small car. If we increase the mass, we're going to decrease the acceleration. You can prove that to yourself in a similar way. Make up some numbers for here. For example, if the force is equal to 10 and the mass is equal to 2, you would get an acceleration of 5. Whereas if we increase the mass, this number right here, let's say we increase it, instead of 2, we increase it to 5. 10 divided by 5 is equal to 2. So when we increase the bottom number here, the mass, we get a decrease in acceleration. Alright, so we can do some simple math problems here. We would write out our formula. Acceleration is equal to force divided by mass. Acceleration is equal to force is equal to mass is equal to. And my acceleration, we don't know that if you read the problem. Let's just read it real quick. A boy pushes a grocery cart forward with a mass of 40 kilograms. 40 kilograms. What's the acceleration? So that's what we don't know. Of the cart when the net force is 60 newtons. Okay. If you weren't in class when I gave these notes, we went through a long process trying to understand why a newton is actually a kilogram times a meter per second squared. And you can either get together with me or talk to a student about that. So the force is 60 newtons, but I'm going to write that as kilograms times meter per second, and per second is the same as squared, is equal to a mass of 40 kilograms. Okay, then over here we'd show our work. Acceleration is equal to 60 kilograms times meter per second squared, those were the units, divided by 40 kilograms. So when I take 60 divided by 40, I'm going to get 1.5. A kilogram divided by a kilogram, those cancel out. So I'm left with meters per second squared as my units. And that sure does make sense, doesn't it? That I end up with meters per second squared when I'm trying to calculate acceleration in the first place. So the acceleration is equal to 1.5 meters per second squared. So what that's saying is, if I have something that has a mass of 40 kilograms, I hit it with a force of 60 newtons, this is going to be how fast it accelerates, excluding all other forces. So that wouldn't include, this would be like in outer space where there is no friction. Okay, so the net force is 60 kilograms. It will accelerate at 1.5 meters per second squared. It's just another math problem to practice. I don't think I need to go over how to do that again, so you can use the previous example to do the same problem. Make sure you have your units and everything like I just showed. And again, here's one more problem just to practice. Now, I've actually shown this in class before, and if you weren't here, I basically drop a golf ball and a ping pong ball, and what happens is if I drop them, it doesn't show up very well. If I drop, let's say that's the golf ball, and here's the ping pong ball. If I drop them from the same height, for the distance that they fall, they actually hit the ground pretty much the same time. Okay? And so now I'm going to explain why that is. So here I have an elephant, and the elephant has a pretty large mass. Okay? And I'm just going to add some numbers to this example. Let's say the mass is 10 kilograms. And the force of pulling it down to the earth is also pretty large. Okay? It has a greater attraction to the earth. So let's say it has a force of 10. Okay? Now, this little person that's falling right here doesn't have as much mass. Maybe it only has a mass of 1. Okay? And also the force pulling it to the earth is also less. There's less weight pulling, less traction between him and the earth compared to the elephant. So that force would also be 1. So notice what happens here. When I take a force of 10 and have to accelerate this heavy, massive elephant, okay, I get an acceleration rate of 1. But when I do the same thing for this guy, okay, the same thing happens. This number got smaller here, and this number got smaller, but they got smaller at the same rate. So I also get a number of 1s. They both would accelerate towards the earth at the same rate. In retrospect, I kind of wish I would have had 100 here, and 100 here, and a 10 here, and a 10 here, because that would get us pretty close to an acceleration rate of 10, which is actually the rate that things accelerate towards the earth. They accelerate close to 10 meters per second squared. 9.8 meters per second squared is the rate that things would accelerate towards the earth. And it does not matter the mass of the object. It doesn't matter the mass of the object because if I increase the mass right here of the elephant, I also increase the force that's being pulled down to the earth. So I get the same acceleration rate. So all I did here was I just give a quick example of what I just talked about. You can calculate the acceleration rate of both the apple and the watermelon here, and you're going to see that they end up accelerating towards the earth at the exact same rate. And so I'll just sort of set it up real quick. So what you would want to do is just do this simple calculation. Acceleration is equal to the force, 1 Newton, divided by 0.102 kilograms is equal to, and then just do the math there and calculate the acceleration. You would do the exact same thing over here for the watermelon. If you do everything right, you're going to get the exact same number, so they would accelerate towards the earth at the same time. Okay, just to muddy the waters a little bit, my golf ball and ping pong ball analogy were not really perfect, because if I drop them from a high enough building, I don't know, Empire State Building or someplace really high in our atmosphere, doesn't even have to be too, that's my building. If I could drop them from a really high place, you in fact probably know that the ping pong ball would in fact make it to the ground after the golf ball. And when I dropped it from a short distance, air friction didn't play too much of a role in how the golf ball or ping pong ball fall. So let's see if I can explain why, if we drop something in the Earth's atmosphere, what we previously talked about isn't exactly observed. Well, I don't want to get it too complicated, but just to remember, the force pulling both the golf ball and the ping pong down to the Earth is the force of weight, or gravity. And the weight of the golf ball is much bigger than the weight of the ping pong ball. And so you know when something falls through our atmosphere, it's air friction pushing back up the other direction that causes the resistance to its fall. And so basically this golf ball will accelerate longer until the force of friction is equal to its weight, and then it will reach terminal velocity. Likewise, with the ping pong ball, it will also accelerate until the force of friction is equal to its weight, and it will also reach terminal velocity. However, the ping pong ball is going to reach terminal velocity much sooner because the two arrows will equal the same size sooner. So this might fall at a slower terminal velocity. I'm going to just totally make up a number here. Maybe it's falling to the Earth. Its terminal velocity might be, I'll just use even miles per hour here, at 10 miles per hour. But this one will accelerate, the golf ball will accelerate until it reaches a terminal velocity of maybe 40 miles per hour. Again, I'm making those numbers up completely, but to illustrate the point that they have different terminal velocities. So in fact, they will hit the ground at different times. However, if you could get rid of friction, they would in fact hit the ground at the same time. All right, so then what we did after this is we took and did part 1 of Newton's second law on pages 3 and 4 of your notes, and that's probably going to end up being, hopefully I'll make a YouTube video of that to help you make up the lab data for that if needed.